Hello everyone, good day. I am SM Shohel Rana and I am a PhD student at Electronics Engineering Department. Today I am presenting a polydead matte functionalized nanofibrous matte-based cell per human motion sensor for IoT applications. Outlines. I will discuss our research motivation, limitation and key factor for solution, review of previous work and challenges, our research approach, working principle and simulation results, fabrication of cell per human motion sensor, and finally I will discuss experimental results, application and conclusions. Motivation. Motion sensor plays an important role in robotic motion, car motion, virtual gaming, human motion, drones, smart home to achieve the function of monitoring acceleration, force, velocity and other motion parameters. According to Global Sensor Market Share 2021, 27% sensor are motion sensor. Most commonly used commercial motion sensor are PIR sensor. Therefore, the popularity of motion sensor increasing day by day. Therefore, it will good opportunities in consumer electronics and automotive industries. Limitation of conventional motion sensor. Existing PIR sensor requires electrochemical batteries, which increases power consumption and complexity because of limited lifespan and periodic charging. Most commonly used electrochemical battery are lithium-ion battery. Among them, 5% lithium-ion battery are recycled and 95% battery are causes serious environmental hazard. That are the limitation of conventional motion sensors. Key factor for solution. Energy harvesting from ambient and environment has attractive research interest for the development of cell per sensor and the reduction of global energy crisis. In past decades, various devices has been developed based on dielectric nanogenerator and piezoelectric nanogenerator. Among them, dielectric nanogenerator is one of the most promising approaches for converting mechanical energy into electricity. Because of lightweight, multiple device structure and easy fabrication. Review of previous work and challenges. Most of the research focuses negative dielectric material to improve the output performance based on device structure, filler concentration, and surface morphology, charge injection, and other methods to improve the output performance. However, they have still some challenges like high sensitivity, high stability, and high power density. Our research approach. We fabricated cell per human motion sensor based on nylon 11 and polydead composite nanofiber. We select polydead as a cationic polymer that mostly improve charge trapping capability and dielectric constant because of microcapacitor formation and functionate with functional group. Polydead can also improve the mechanical properties because of van der Waals attractive force between the polydead and nylon 11. Therefore, it provides high stability, high mechanical strength, and high sensitivity. Fabrication sequence of cell per human motion sensor. We fabricated nanocomposite nanofiber prepared by electrospinning process. Nylon 11 and polydead composite act as a type of positive material and PVDF TRFE act as a type of negative material. Nylon coated conductive fabric is used for electrode because of high conductivity, and Kapton strip are used to create deformation consistently. And finally, acrylic sheet we use as a substrate. Working principle and simulation. Initially, two dielectric layers are separated from each other and maintain neutral state. Under external pressure, two dielectric layers are brought into contact and generate charge because of dielectric effect. During releasing, compensating charge are generated between top and bottom electrode, and electron will transfer from bottom electrode to top electrode and generate negative voltage. During periodical contact and separation, it will generate AC signal. Final element method are used for potential distribution at various gap distance. Gap is an important parameter to optimize the output performance of our sensor. Therefore, we measure transfer charge and it will linearly increase up to 2 mm and after that saturated. Therefore, we select 2 mm gap for our sensor. Experimental result. We measure dielectric constant of pure nylon with different concentration of polydead 33% weight percentage polydead shows the maximum dielectric constant. It increased 2 times. Furthermore, we investigate surface potential and mechanical properties of pure nylon and nylon 11 polyethylene composite. Surface potential increased 2 times and Young modulus increased 6 times, and finally tensile strength increased 3 times of our composite nanofiber. We measure electrical output performance with different concentration of polyethylene, and it increase up to 33% polyethylene, and it shows maximum output voltage around 380 voltage because of microcapacitor formation. It mostly improve the charge density of the composite nanofiber, and after that it decreased because of conductive effect. We also measured the output performance with different nanofiber and film, and composite nanofiber shows the maximum output performance. We also measure sensor performance with different frequency, and our sensor shows resonance frequency 12 Hz frequency, and after that output performance decrease because of air breakdown. And we also measure sensor performance with different pressure, and our sensor shows optimized pressure is 36 kilopascal, and it provides maximum contact area. After that output performance saturated. We also measure output performance of our sensor with different acceleration, and 1 Hz acceleration shows the maximum transfer charge, and after that transfer charge decrease because of strong drag force of our Kapton strip. Our sensor shows maximum power density 7.6 watt per meter square. Therefore, we investigated stability test of our sensor. Our sensor shows high stable output up to 76K cycle without any measurable degradation. Therefore, we investigated sensitivity of our sensor. Our sensor shows sensitivity 1.01 volt per kilopascal, and also our sensor capable to detect pressure in 0 to 50 kilopascal pressure. Application: we develop a wireless system architecture for cell per human motion sensor. Our sensor provide electrical signal to op-amp, filter circuit, signal processing unit, MCU, Ethernet, and Wi-Fi. Finally, a smartphone have been used for monitoring human motion for wireless IoT application. Demonstration: real-time human motion monitoring. We put our sensor on floor, and it can detect human motion for real-time IoT application. Here we can see the video demonstration. Furthermore, we put our sensor on steer, and depends on human motion it control automatic steer light for smart home application. Here we can see the video demonstration. Furthermore, our sensor was attached on stock for monitoring different type of human motion like walking, jogging, running, and jumping. And finally, our sensor can able to detect walking step. Here is the output signal of walking step. In summary, we fabricated cell power human motion sensor based on dielectric nanogenerator. Therefore, we developed a novel nylon 11 and polyethylene composite nanofiber as a positive dielectric nanofiber. Our device shows high sensitivity output performance is around 1.01 volt per kilopascal, and also our device shows excellent mechanical stability. And finally, we demonstrate real-time human motion like walking, jogging, running, and also posture monitoring. Acknowledgement: this work was supported by National Research Foundation of Korea, grant funded by the Korea government, and we are also grateful to the member of Advanced Sensor and Energy Research Lab for their technical support and discussion. Thank you for your attention.